Gets me every time. Good enough. All right. When is the first assignment due? Well, it is due on the 31st of January. So there you go. Cool. Yep. So, hello everybody, good morning. Nope, that's incorrect. It is January 31st. Yep. So assignment 1, we've put it up on Avenue. We are still having a little bit of trouble getting the having a little bit of trouble getting the system together. So Jupyter's hopefully by the end of this week we will have Jupyter all together. It's been just a whole bunch of grossness. We'll post an announcement when everything's working. Essentially, the problem is that certain parties in their infinite wisdom thought that we might be able to reuse configuration settings from last semester this semester to save some time and to save some work. And of course, the problem with computers is that sometimes when you're attempting to save yourself time and effort, all you do is you end up causing yourself more time and effort. And this is one of those situations. So, yeah, you know, yeah, we can go over that. So, yes, you should be seeing that a lot at this point. I guess I'll lead off with that just because it's probably of interest to the whole gang. So, if it is relevant, knowing how to define a function is always relevant. So, we do end up talking about functions. The rest of this lecture is kind of soft material, and yes, you can use Jupyter on Anaconda rather than on the Mac server. Yes, absolutely. That is the whole point of having them distributable through Avenue as well. So, I'm going to assume that you know nothing about programming, but you do know what a function is in a mathematical sense. So, you know, casting your brain back to high school, you will have some impression of what a function is, because you took advanced functions in high school. So we can think of something like, for example, sine, like the trigonometric function sine. That's a function, right? You provide it with an input, and you receive from it an output. Generally speaking, when you're talking about functions in a mathematical sense, you're talking you can graph them, right? You've got your input is typically x, and whatever your output is, that's typically y. If it's a sine function, then, you have that nice oscillation that goes on relative to the y value is moving between whatever the amplitude of the function is. In most cases, 1, unless it's been multiplied by something. So you've got an input, and you receive an output, right? A function in programming has a very similar aspect. With functions, you provide inputs and you receive outputs, right? When you write a function in Python, another good way of thinking about it is as a subroutine. There's a technical difference between a function and a subroutine in programming, but that's kind of immaterial at this point. A function is a piece of code. It's like a small program that is packaged up and provided and given a name, right? So it's like writing a sub-program within your program. The advantage of doing this is that you can then execute that sub-program whenever you use the function, right? So what happens when you use a function in a program is the program notices that a function has been called. It takes whatever you've given that function as arguments. It plugs those into the actual function definition, executes this function, and then whatever the return value is, it takes that and it substitutes it in for the function call within the regular execution of the program. So let me show you what I mean in the Python interpreter, the handy dandy Python interpreter. So the Python interpreter, for those of you who are still coming to grips with all of these things, this is just a way for me to enter a program in one line at a time and have it execute in real time. It's very handy. So if I want to define a function, say add3, I then have to say what I want to call the three. In add3, I want to take 3 inputs, add them all together, and return whatever the result is. So I need 3 arguments to this function. Arguments or parameters. We'll call them x, y, and z. Within the context of this function, x, y, and z are these are what we call formal parameters. So if I write return x plus y plus z, I have defined the functionality of this function, so to speak. So now we have add3. Add3 is a function that has been defined within the sort of program space within the program that we're working. When you're working in the interpreter, there's off to the side, there's a list of all of the things that have been defined that the thing keeps track of. So, for example, if we want to see what the type of add3 is, you can see it is a function, right? We haven't seen the type function yet, but you can use it to decide what the type of anything that you put into it is. So if we want to use a function, add3, we have to provide it actual parameters. If we just call it like this, it says, I'm missing 3 positional arguments. You have not given me the inputs. So you have to give them the inputs. Say 1, 2, and 3. The result is 6. And the interesting thing about function calls is you can actually integrate them into larger expressions. Right? So what happens in programming, what actually happens when it wants to evaluate the expression add 3, 1, 2, 3 plus 9 divided by 3, it'd probably do this one first because it probably it'll bind things according to bed mass, right? So it'll calculate that. That'll be 3. And it's like, okay, I need the result of add 3 on 1, 2, and 3, and then add 3 to that. right? And this actually makes it into a floating point as well. That's why you get the 0.0. So what it does is it says, okay, so x is assigned the value of 1, y is assigned the value of 2, and z is assigned the value of 3. It then goes through all of the statements inside of this function, in this case just the return statement, and it executes them. When it hits a return statement, it's like, okay, function is now exiting with this value. So, since this is the expression x plus y plus z, it will evaluate this expression. So 1 plus 2 plus 3 is 6. So the return value of the function is 6. So 6 gets substituted into this expression right here, and then 3 is added to it. 6 plus 3 is 9, and that's the result. So that's how a function works. Okay. Is everything indented on the next part of the function? Yes. So everything that's inside of a function is indented one level from the definition of the function. Yes. Why does it become floating point? Because this is a floating point operation. So technically speaking, if you want a floating point result, you use single slash. If you want a integer result, you use double slash. It's not super important to know the fine details between integer and floating point representations. We'll get there eventually. In fact, we're going to get there pretty shortly. But yes, that's, we'll get there. But yeah, it has to do with the manner of the division. If you add a floating point number to an integer value, you will automatically get a floating point value back, even if the floating point value is, a whole number. It doesn't really care if a floating point number is a whole number or not. All it cares about is whether or not it has been defined as a floating point number. So, how do you make things become a floating point when you input them into a function? Generally the position that Python takes on floating point numbers is to try to not worry you about it whenever possible. That's why you get these smooth transitions between, adding integers and floating points and that sort of thing. I mean, I believe you can do this. Yeah. So if you would like to perform explicit conversion between integers and floating points, let's see if this works. Yeah. So if you just use the name float or int as a function and you call it on whatever you want to convert, then that works. Whoop! My goodness. Sorry about that, guys. I'm balancing this guy on a book. I'm actually balancing it on a biography of Winston Churchill. Because that's a nice, thick book, Cool. Do those X, Y, and Z carry over as X, Y, and Z, or is it just in that moment? Very good question. So X, Y, and Z are only defined within the context of the function. So if exterior to the function, I try to use a value that was in the function, try to read its value, it says name error, X is not defined. X does not exist outside of the context of the function. In programmer speak, we say that it is local to the function. So that means you can't get at it from outside of the function. Good question. How do you stipulate what you are allowed to enter into the function? In Python, it's difficult. Generally speaking, as your colleague mentions, generally speaking, in Python, there's not a whole lot of way to restrict what can be entered into the function. However, you can write stuff like if type is equal to if type of x is equal to type of 0.1 to see if it's a float or not, right? There are ways of manually checking whether something is a floating point or number or not. However, unlike a lot of other programming languages like C, in Python, arguments to functions are not statically typed. This is a dynamically typed programming language, which means that you can pretty much enter any type of data that you would like into a function as an argument. You're just kind of expected to use a function in the expected manner, if that makes sense. So that's why documentation becomes so important. Like, for example, perhaps you didn't know this, but if you type help and then provide a function name, it will actually show you some documentation on how a function is expected to be used. So I think Q quits. So if we take a look at the max function, you can see it takes a certain number of arguments, or it takes an iterable, and it just takes the biggest item. You can get some description of how the function is supposed to be used and what it's supposed to output. So yeah, it's not strictly defined in Python, which actually causes some problems, but yes. Can you change the number of decimal places? Yes, you can. We'll get into all of this when we start talking about floating point. For now, let's continue on with our lecture topic. So, at the end of last lecture, I was getting very excitable because I saw a picture of an old computer, and I was like, old computers, all kinds of fun stuff. But there are some very important points in here that you need to know about in order to understand how a computer works. Basically, what this section is trying to tell you about is how do computers work, sort of from a top-level perspective, right? So, essentially, pretty much the vast majority of computing devices, that you will be either interacting with or thinking of as computers. A lot of people don't think of their kitchen timer as being a computer, but it totally is one. People just don't tend to think of them as being computers, but they do compute things. These will be using what's called the von Neumann computer architecture. This is the CPU memory interaction or interface, right? So a computer is a device which takes input and produces output. The input is received in one of several different ways. It could be keyboard input, it could be mouse input, it could be touchscreen input. All of these things count as input. It then goes into the central processing unit. Operations are performed. The memory is interacted with. And then whatever the results of those calculations are, you have some sort of interpretation of that that's sent to an output device. Output devices most commonly being things like monitors and speakers and printers and such things. This is sort of the very basics of computation. So within the central processing unit, you have a portion of your CPU that is strictly in charge of managing memory. So making sure the right data is in the right circuit at the right time. Very important stuff. Control unit. Then you have the portion of the CPU that actually does the calculating. When you add two things, it's the circuit that adds two things. We won't get into the binary representations of these types of things, but if you're interested in that sort of thing, I have a lecture way back in... if you take a look at the lectures that I did on assembly programming in 2MP3 last semester, then you'll be... That should be very interesting to you if this is the sort of thing that interests you. Memory unit, this is like... There's a lot of different types of memory that exist inside of your computer. Some of the memory is like integral to the CPU itself. We call that register memory. You then have RAM, RAM is like your RAM chips. This is like the operational working memory of the programs on your computer. And then you have the hard drive, or permanent memory, or read-only memory, as it were. These are arranged in order of speed. So the registers within the CPU, very, 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 very fast, but volatile. That is to say, the memory inside them can actually decay over time. That's why, but it doesn't matter because it's getting, like, the memory there is getting refreshed, several thousands or millions of times per second. So it doesn't matter if the memory only lasts a second, right? The RAM lasts much longer, but is much slower to access, and the ROM lasts the longest, years or decades, but it is the slowest to write. So that's, in general, if you're talking about the underlying electronic circuits, there's a trade-off between the permanency of the memory and how long it takes to use. So ROM lasts the longest, but it is the longest to write to, and register memory it lasts the shortest amount of time, but it is the fastest to write to, generally speaking. Questions? Yep. So, CPUs operates. So, computer memory is stored exclusively in binary data. So, every single piece of memory inside of a computer, without exception, is stored or interpreted as either a 1 or a 0. 1 or 0. That's it. Ones and zeros. Everything is ones and zeros. Absolutely everything. Ones and zeros. The way that this gets interpreted in terms of electronics is as high or low voltages within circuits, right? So if you have a memory cell, that memory cell is carrying either a high voltage, like 5 volts or 3.3 volts, something like that, or a low voltage, which would be 0 volts or very close to 0 volts. These electrical potentials can be used to actuate transistors. That is to say, high or low voltages can flip these tiny, tiny little electronic switches inside of your CPU, which are known as transistors. And that's how computers work, essentially. But it's very important to know that every single number is a binary number. You can actually see this in Python if you use the bin converter. It will convert your number. Well, technically what it's doing is it's producing a string that represents the underlying binary representation. This is one of the multifarious ways in which I hate Python, because rather than just show you the binary number, they think, oh, we'll just use a string to represent ones and zeros as characters, which expands out the representation of the number by a factor of 8, which is ridiculous because, why can't I just get at the bits? But I think if you do, yeah. So if you ever want to enter a number into Python in binary and then get out what the integer representation is, for instance, if you hit 0b, you can then enter a binary number directly, and it will tell you what that is as stored on your computer. So that's kind of cool. But everything is in zeros and ones. Everything. So there you go. CPUs have their own very limited memory called registers. So the main operations that your CPU is performing on a sort of continuous basis, I'm, executing several million of these instructions per second just to be able to send this information to you right now. Loading memory into registers, performing arithmetic operations on registers, storing data from registers back into the memory, and jumping around which instruction I'm on. When you write an if statement, what you're actually doing is you're performing a manipulation on what's called the program pointer. So if you imagine a program as a list of instructions for the CPU, right? There is a register that keeps track of which instruction you're on. performing an if statement, all that's doing is it's manipulating the program pointer. So it's saying, okay, you know, on this condition, I will jump to this, you know, set of operations and then jump out or jump later. And in the other case, I'll jump to this different block of instructions, execute that until the end, and then jump back out again as well. So, you know, when things, you know, at the very basic level, computers do very simple things very quickly, I guess, is the sort of way of thinking about it. Originally, people had to program in that type of language directly. Around the, you know, I'd say a couple of decades maybe after the initial development of computers, people were like, you know what? Programming, like this type of programming really sucks. It's so tedious and you can barely accomplish anything. What if we got the computer to handle some of this for us? So then you have the development of programming languages. So what we have now, something like Python, this is a language that gets compiled. Well, actually, technically, no. Better example would be C. So a program in the C programming language. C is one of the most basic programming languages and one of the older ones. It gets taken into another program that parses it out. You know, it interprets it interprets the code that you've written and generates all of the machine instructions. Those machine instructions are stored in an executable file, and you can then choose as the user to run that executable file, right? But it's very important to understand the distinction between the machine code and the program that you've written. You know, even for a very simple programming language like C, the machine code that's generated from the code that you've written can be, you know, many, many times as the numbers of instructions as there were in the original program. So how things work with Python is essentially Python compiles in real time. In Python, when you choose to execute a Python source file, you do so, like the operating system will run the Python interpreter, is what it's called, but it's like a program that you feed Python instructions into, and it just performs the instructions. It's like real-time compilation, if that makes sense. So there are advantages and disadvantages to this. Because it does this way, you don't have to worry about compiling a Python script or a Python program for a bunch of different operating systems. As long as you've got the Python interpreter working on that operating system, the Python scripts themselves can be transported across many, many different operating systems or environments. This is, in a lot of ways, very similar to the idea of the Java virtual machine. I know a few of you have programmed in Java before. One of the great advantages of Java is that as long as you've got a thing on which the Java virtual machine runs, you can run any Java program on that platform, right? Python uses that type of model as well. However, one of the disadvantages is that Python doesn't know that your program has an error until it hits the line where the error is. So in order to actually see if there's an error in your Python file, you have to actually encounter that during runtime. So one of the consequences of this, let's say you write an if statement and one of the branches is just never executed because the condition never comes up, right? If there's a syntax error inside of that branch that's never executed, your program will never find it. So if that condition ever eventually does become the case, and that syntax error, the Python interpreter tries to run that syntax error, it'll just flunk out on a runtime error, and whoever you wrote that program for will not be pleased with you. I can tell you, but and that includes the autograder. So yeah. Anyway, so you have Fortran. Fortran was one of the very, very early languages that were written for computing devices. It stands for Formula Translator, and this is what an if statement looks like in Fortran. This is a punch card. After that, we had the development of other programming languages, such as Algol, Pascal, COBOL is an older one as well. And in the early 70s, C. C is a very important programming language. People had no idea how popular it would become when they originally made it. It's many of the operating systems that you use today have their basis in C. C became the language of choice for writing operating systems at the time when operating systems were a new concept, if that makes sense. Prior to the existence of operating systems, all you would do would be to run a program, right? There was no drop down of programs installed. There was no idea or concept of that you could install a program in an operating system. There was no concept of file system management. A lot of the file system management stuff was developed during this period in computational history. Like the 70s, man, to be a programmer during the 70s, it's probably not an overestimate to say that the programming work that was done in the 70s will carry through until the end of human civilization. We will be out in our spaceships colonizing the far reaches of the galaxy, and, somewhere on that spaceship there will be C programs that were written by, whoever back in the 1970s. But anyway, so in recent years there's been a kind of shift towards quote-unquote graphical programming languages, which a few of you have probably used. They've become popular in educational circles. I don't really know any names of them personally, but they're these languages where you've got blocks and you click them together and that makes programs. Generally speaking, real programmers don't use them because they're not fast enough. It doesn't matter how good you are at graphical programming, you'll always be able, a good programmer will always be faster on a keyboard. So, that's why, although, people think that, eventually graphical language optimists think that eventually graphical languages will overtake, programming, it's unlikely, just because of the speed factor. I'm going to take a look at seeing... Oh, Scratch! Yeah, Scratch. Thank you, yeah. Maybe I can take a look and see what... let's see. Scratch programming language. For kids! Ha! Oh, yeah, okay. Yeah, this kind of stuff. Absolutely this kind of stuff. So, Flappy Fish in Scratch, right? Yeah, so you've got, they're puzzle pieces and you click them together. There are also, various programming games that you can see where it's write a program to make the robot walk the maze and that sort of thing. generally speaking, not fast enough for practical purposes. Although, you know, what language is used to analyze Scantron cards? I'm not sure. It's probably something pretty low level. I would think probably C++ or something. Yeah, they're good for learning the basics, but like, it's kind of like oh, what's a good analogy for that? Yeah, they're kind of like beginning books for people who are young and are learning how to read. You know, it's like C spot run, run spot run will get you so far, but no further. You know, although in programming it's kind of a technically different thing because we have this idea that lost my train of thought. In programming, we have an equivalency between programming languages. We have a concept of equivalency between the programming languages. So basically, how it works is, as long as you've got if statements and while loops, and you have the ability to write a program that never terminates, your program is what's called Turing complete. This means that there exists an equivalent representation inside of a Turing machine. So this means that any program that's written in any programming language that's Turing complete can be written in any other programming language that's Turing complete. So long as Scratch is Turing complete, you can write any program inside of Scratch. The question, though, is would you want to? Because basically the thing, and we're actually going to get, this is actually related to the lecture topic, within programming languages, the correct way to think about programming languages is as tools, right? You have a task, and you want to select the correct tool for that task, right? Sometimes the correct tool is Python. Sometimes the correct tool is C++. Sometimes the correct tool is R or Haskell. There's like, you know, if you're doing really low-level memory management type stuff and you want it to run very, very efficiently, the correct tool for the job is C. If you just want to get something working quickly and you don't necessarily care about the efficiency, I recommend Python. So, you know, always, like, if you embark on a programming project, what is the right language for the thing I want to accomplish? If you are writing a video game, it is probably a good idea to start with a video game development environment, right? You can write, like this game that I released on Tuesday, Hexy. I totally could have done that in C++ if I had wanted to, but the number of man-hours of work that I saved by writing it in Unity rather than in C++ are manifold. It probably would have taken me at least 20 times as long to write that game in C++ as write it in Unity. But yeah. What's the difference between high and low level languages? Oh, yeah. Actually, I have a slide on that. I should just do the slides. I already talked about compilers. Okay. So, yeah, here is the slide. So, you'll hear people like me talk about the difference between high-level languages and low-level languages because it's an actual distinction. So, the higher level a language is, the more abstractions it has built into it. So, the rough correspondence is how many machine code instructions are generated per line of this programming language, right? So something like Haskell generates a lot of machine code for any particular line of code in Haskell. But the thing is, you can express in 4 lines of Haskell a program that takes at least 50 lines in C, right? So the advantage of high-level languages is compactness and expressivity. So you can perform more complicated functions more easily in a high-level language than in a low-level language. I would actually argue that Python is kind of in the middle. The only reason people consider Python a high-level language is because it has a lot of libraries. It has a lot of pre-built functionality into it. Although I guess you could also make the argument for the manner in which it handles things like lists and dictionaries is very, like, you can handle those quickly with very few lines of code using Python's abstractions, which are very useful. But you should understand that the higher the language is, the more removed you are from the underlying machine, right? So the lower level the language, the closer you are to the bare metal. Bare metal means like the electronic circuits itself. So if you get a programming language like C, in C, you are responsible for all kinds of memory management stuff that that Python handles in the background and says, you know what, I'm going to take care of how this is represented in memory. Don't you worry about it. I got you, man. C is like, nope, I'm not going to do a single thing with memory unless you explicitly tell me to do so. One way or another. And, the advantage of a high-level language with respect to memory management is you don't have to worry about anything. You can just program. You can focus on the thing that you want to do. The disadvantage is a machine is never going to be able to do it as efficiently as you can if you know what you're doing. So if the memory interactions in your program are what's slowing it down, and it's necessary for you to write a fast responsive program, you're going to want to do that in C or assembly, right? The lower the level of the language, the more direct control you, the programmer, have over the actual instructions that are actually executing on the CPU, which means that you can eliminate redundancies, you can improve the efficiency of the memory management, you can do all kinds of interesting things to make your program run fast. That's why it's super, super important that portions of your operating system get done this way. Basically, the more times, the greater the frequency with which a subroutine is performed inside of a computer, the more you should want to do that in a low-level language, because low-level languages are the most efficient. The drawback, though, with low-level languages is that they tend to be much more complex things to try to use. Because you don't have all of the abstractions that are available to you in something like Python or Haskell, you have to know how to do all of that stuff by hand, and so to speak. And, that can be complicated. Assembly programming is particularly brutal. We had a little bit of assembly programming in 2MP3 that I taught last semester, and in terms of something that's like a testable problem that I could give them in assembly, it was like the baby first assignment programs that I had them write in C that were basically like, can you compile a program that does almost nothing? That's the level that is a difficult problem in assembly. So, merely doing something like the Collatz conjecture is a very difficult thing to do in assembly. It's challenging. Anyway, hopefully that's an answer to your question. C++ is object-oriented. Yep. What's the difference between C and C++? C++ is C++. C++ builds in a large number of abstractions and features that were never done in C. bringing it up to the level of abstraction of sort of medium-level programming language like Java. However, the interesting thing about C++ is that all C programs, or almost all C programs, are valid C++ programs. So, yeah, there you go. Showing up to NASCAR with a go-kart. Yes, that's a good one. Would it be right to say that high-level languages are more independent? It depends on what you mean by independent. Rejected Python becomes assembly code. Well, maybe. Yeah. Anyway, let's move on. So another distinction that we make with programming languages is that you have general-purpose language versus application-specific languages. These are sometimes called DSLs, or domain-specific languages. So, for example, HTML is not a programming language. That's the programmer's joke, is like, HTML, like people who know nothing about programming think that HTML is a programming language when it's not. It's a document language. It's like fancy Word. It's not a programming language. So HTML is used specifically for making web pages and for nothing else. SQL, which we'll be covering a little bit of in this course, that is only used for databases and used for nothing else. R is a language that's used only for statistics and statistical analysis, and it is used for nothing else. Programming languages like Python, C, and Haskell can be used for lots and lots and lots of different things. As we're going to see, Python can do all of these things, right? It's like, the analogy is like wrenches, right? So let's imagine that you are trying to undo a bolt, right? You could, go into your toolbox and find the, specific wrench size for the specific bolt that you're doing, and if you do that, it is likely that you will, if you get the correct size spanner for a particular bolt, it'll be the easiest to undo that bolt with that spanner. However, if you, like what most of us actually do, is we just reach into the toolbox, get the adjustable spanner, because that's the one on top, and then, adjust the adjustable spanner to the particular gauge of the bolt and just undo it that way, even though you have to, sometimes in the middle, you have to retighten it, depending on how good your adjustable spanner is. A lot of the time, like Python in particular is a great language for just like, let me just do this quickly. I don't want to make the Taj Mahal of programs here. I just need a task done quickly. For general purpose stuff, Python is a good language. C is a general purpose language because it, anything that can be done in C, basically. And, but anyway. Oh my goodness. Am I seriously not going to finish these today? So the other thing, I already touched on this idea as well. You have a difference between interpreted and compiled languages as well. So interpreted languages have a program that's sitting in the operating system that you put your instructions into, and it does its stuff. With compiled languages, you take your entire program, feed that all into the compiler at once. The compiler churns and figures it out, spits out an executable, like a set of machine code instructions, and then you separately invoke those machine code instructions to be executed. The advantage of doing it that way is that it's much faster. The advantage of doing it the first way is that it's easier to debug. Hypothetically speaking, I'm not convinced, but, mileage may vary. So, in addition to that, you've got three main schools of language. It's kind of like in D&D. We're talking about the different schools of magic now. So you've got declarative or functional languages. These are programming languages like Haskell. If they're for the two people in comp sci in this class, this is the type of language you learn in 1JC3. Basically, the way a declarative language works is you say what the program should produce, and the program figures out how to do it. With imperative or procedural languages, such as Python and other object-oriented languages, you are programming in instructions. You tell the computer what to do, not what you want, right? So these tend to be the lower level languages, whereas declarative languages tend to be the higher level languages. So imperative, procedural, you are writing instructions, and then logic languages are you are expressing mathematics more purely. They don't come up much. The general example is Prolog. It's like there's only a handful of them, and they're not commonly used outside of academic settings. So, although they're used a little, but not generally. Generally speaking, you probably don't have to worry about them. Okay, so it's now 10:21. I will answer any questions you have. I have office hours immediately following the lecture, although I'll probably make myself some tea. So, yes. Is the assignment on Avenue due the 31st? Yes. Boomers love to use R for other things other than data science, though. Well, I mean, I can't, it is beyond the scope of this course for me to explain boomerism. Okay, thank you. Yep. Is Minecraft Redstone logic Turing complete? Good question! That's one for the Googs. Gotta ask the Googs that. Is Minecraft Redstone Turing complete? Yes! Yup. Minecraft Redstone is Turing complete. So you could make... And people have done this. People have made computers that run like Windows 95 in Minecraft. However, it's kind of like that universe simulating a universe problem, that the universe that's simulating the universe has to be much larger than the universe that is contained. The other one that you can do this in is Dwarf Fortress. If you do fluid mechanics in Dwarf Fortress, they are also Turing complete. Is Python used in corporate settings, or are other languages more prevalent? It really depends on what you want to do. If you're working for an old company that has lots of existing code base, then you're probably looking at C++, my friend. If you're looking for one of these hip new startups that doesn't have an existing coding base, and they're like one of these agile development guys who are just looking to get something running quickly, you'll probably end up using Python. What's the best way to troubleshoot code in this class? Yes, good question. I recommend Python Tutor. Python Tutor. Blammo. This is your general purpose. This is your general purpose debugging software. So, like, for example, if I did def add x, y, z, return x plus y plus z. See how much faster that is than Scratch? Add, print, add, 1, 2, 3. Visualize execution. You can actually scroll through all of the lines of code here, and it shows you how they get executed. See, the return value is 6, then it prints 6. Like, this is super, super, super useful. Use Python Tutor for debugging stuff. 100%. Like, The only problem with it is that its size is limited, but that shouldn't be a problem for any of the things that you are doing in this class, unless you are doing them very inefficiently. It should be fine. What's the in and out thing in Jupyter? Talk to me at office hours for that one. Python, Minecraft Redstone runs faster than Python. Oops. Can you do your assignments in Minecraft? No. No, it has to be in Python. Some crazy guy remade the entirety of Pokemon Red using Minecraft command blocks. And yep. Well, you know what? The interesting thing about those, like, really old games, right, is, like Pokemon games are only a few kilobytes, I think. Let's see. Memory size of Pokemon Red. Ha! The ROM size for it is only 512, or in North America, 1 megabyte. So, you know, it would take some time for sure, but it's conceivable if you had a team of people working on it that you could manually manually set all of the bits that are in the ROM file for Pokemon games in something like Minecraft and run Pokemon in Minecraft. Absolutely. Absolutely, my friends. As an alternative to Python Tutor, Thonny is an X editor, which is really good for that. Yeah, sure. That's the thing, is like, especially with a well-supported language like Python, there are going to be 100 squintillion different good editors out there. I don't even care which one you use. Just make sure that when you have your solution finished, that you put it into the assignment, the Jupyter assignment file, because we will not mark anything that's in Python files. Like, if you submit me like 15 squintillion .py files, you're getting 0, my friends. 0. You've got to put it in the assignment workbook file. Thank you. However, I don't mind if you actually do the development outside of the assignment file. You just have to make sure it's in the assignment file to be submitted. And also, I would appreciate if, when you copied things in, you also ran those things to make sure that they actually run inside of the workbook environment. Thank you. Yes. Also, don't rename the files, please. Don't rename the workbook files. Please. Good Lord. How many people I had last semester who, like, were putting their name and student number on the submission file. Do not put your name and student number on the workbook file that you hand in. Ever, for any reason. Do not worry about it. The way that it's handled is that everybody gets their own folder on the server, and that your Mac IDs are on the folder, so don't worry that we'll lose your assignment file or it won't be attributed to you, because that's all taken care of that's all taken care of by the submission mechanisms. You do not, this is not an English class where you have to put your name on the file of your essay. This is a programming class where we know that it was you that submitted the file, because when we look in your submission folder, that's where the file is. Okay. Anyway. Oh, look, only about half of the class heard that. Anyway, I'm gonna have office hours. Oh, jeez. That's twice now. I should bang the desk less, eh? Or find a slightly larger book. Anywho, office hours next. I'm making tea. Keep it real. Keep it real, my friends. Keep it on the down low. Keep it on the hizzle, faux shizzle, etc., etc. Take her easy.